Hello everybody, this is Hari Krishna, Assistant Professor of Chemistry, Department of H&S, Annamacharya Institute of Technology and Sciences, Tirupati. Today we will discuss of unit number 4, that is instrumental methods and applications. So after completion of this unit, you come to know how to separate the liquid mixtures and gaseous mixtures. Along with that, we can determine the concentration of solutions and rate of reaction. You can analyze the urine and we can determine the metals which is present in the drinking water. We can detect the functional groups and also identify the unknown compounds. So before entering into the subject, first, what is spectroscopy? Spectroscopy is an instrumentally aided study of the interactions between matter and energy. Matter means sample being analyzed and energy means electromagnetic radiation. So coming to the electromagnetic radiations, so the radiations which are having both electric and magnetic field which are perpendicular to each other and are coplanar are called as electromagnetic radiations. These radiations are produced by the oscillation of electric field and magnetic field. Then coming to the characteristics of these electromagnetic radiations. So these are characterized by their wavelengths or frequencies or wave numbers. Here the energy carried by an electromagnetic radiation is directly proportional to its frequency. And the emission and absorption of radiation is quantized and each quantum of radiation is called as photon. All types of electromagnetic radiations travel with the same velocity. No medium is required for their propagation. When visible light is passed through a prism, it splits up into 7 different colors. So this phenomenon is called as dispersion. Then coming to the electromagnetic spectrum. So the arrangement of all types of electromagnetic radiations in order of their increasing wavelengths or decreasing frequencies is known as electromagnetic spectrum. Electromagnetic radiations are absorbed or emitted or propagated in the form of energy packets called as quanta or photons. So each photon has an energy E, so that is equivalent to E equals to h mu, that equals to hc by lambda, where h is Planck's constant, lambda is the wavelength. Then coming to the loss of absorption. So in this loss of absorption, when a beam of light, radiation is passed through a homogeneous medium, the radiant energy may be partly or entirely absorbed, transmitted, reflected and scattered. That is given by an equation IO equals to IA plus IT plus IR, where IO, IA, IT and IR are intensity of incident light, absorbed light, transmitted light and reflected light respectively. So the process of absorption mainly depends upon molecular structure of the solution, molecular structure of the absorbing species and concentration of the solution, light of the path. So here the absorption of light in the visible and near UV region is governed by a photophysical law known as Lambert's Beer law. It is a combination of two laws, that is Lambert's law and Beer law. So first Lambert's law. So Lambert's law states that when a monochromatic light passes through a transport medium, so the rate of decreasing in intensity with the thickness of the medium is proportional to the intensity of light. That means uh, the, the rate of decreasing in intensity is directly proportional to the intensity of light. So that is given by a mathematical expression, that is minus di by dx equals to ki, where I is intensity of radiation, di is small decreasing intensity of radiation, minus di by dx is rate of decrease of intensity of radiation with the thickness, where k is proportionality constant. And next, Beer's law. This law states that when a beam of monochromatic radiation is passed through a solution of absorbing substance, the rate of decrease of intensity of radiation with thickness of the absorbing solution is proportional to the intensity of incident radiation, same as Lambert's law. That means here the decreasing of intensity of radiation with thickness is directly proportional to the intensity of incident radiation as well as the concentration. That is also given by a mathematical equation, that is minus di by dx equals to k dash into IC, where I is in intensity of incident radiation, C is the concentration. Then coming to the colorimetry. Colorimetry means it's a light sensitive device. It's a light sensitive device which is used to measure the transmittance and absorbance of light passing through a liquid sample. So this device measures the intensity or concentration of the color that develops upon introducing a specific reagent into a solution. That means when a solution which is placed in this colorimeter, it develops a color. That means it gives depending upon the wavelength of that solution, the instrument gives color. Then coming to the principle of colorimeter, this law states that the light absorption when passes through a medium are directly proportional to the concentration of the medium. That means that when light passes through a medium, which is directly proportional to the concentration of the medium. In colorimeter, there is a ray of light with a certain wavelength is directed towards the solution, and it involves the quantitative estimation of colors. That means it estimates the color which is present in the sample which we have taken. So the concentration of the colored complex is directly proportional to the concentration of the component in the sample. The difference in color intensity results in the difference in the absorption of light. So the difference in the color intensity, that means if the absorption of light is more, color intensity also more. Coming to schematic diagram of this colorimetry, it has a light source and collimator. When we are passing a light into the collimator, it passes through prism, and in that prism it is dispersed into 7 different types of colors, that is VGR, and it is passed into sample solution which is placed in between there, so which gives that it gives a signal which is detected in the detector. So this is the instrumentation. Coming to the here instrumentation, colorimeters are used to detect color and determine the solution's concentration. That is, when a wavelength is passed through a sample, some of the light is absorbed and some of the light is passes through it. So it is the wavelength of light that passes through that are detected. That means when a light is passed through a sample, some of the light is absorbed and some of the light is transmitted. So here this instrument, the wavelength of light that passes through that are detected by this instrument, that is colorimeter. So the colorimeter uses the Beer-Lambert's law to detect the absorbance of light. So Beer-Lambert's law can be written as A is directly proportional to Cl, where A equals to epsilon Cl, where A is the absorbance, E is the molar absorptivity, C is the concentration of the solution, and L is the length. To measure the concentrations, the amount of light absorbed is dependent upon the amount of solute in the solution. So in order to measure the concentration, the amount of light which is dependent on the amount of solute in the solution. A higher concentration of dissolved solute means the more light will be absorbed. If it is less, means less light will be absorbed. Then coming to the applications So here calorimetry is it has wide range of applications in chemical and biological fields. So it is widely used in analysis of blood. So it's also used in the analysis of water. So water analysis we can use this calorimeter. So what are the nutrients present in soil we can determine by using this calorimeter. We can use to measure the food stuff. Determine the concentration of solutions. By using calorimeter we can determine the concentration of solutions, and also we can determine the rate of reaction by using this calorimeter. By using this calorimeter we can determine the bacterial growth of bacterial culture. So these are the applications of calorimeter. So these are mainly used in the analysis of blood, analysis of water, nutrients in soil, foodstuff, determining the concentration of solutions, determining the rate of reaction. And next topic, that is atomic absorption spectroscopy. So atomic absorption spectroscopy means it's one of the sensitive analytical techniques available for the determination of elements which is present in the given sample in nanograms and picogram levels. That means it's a sensitive analytical technique available for the determination of elements, that is most of the metallic elements are non-metals like phosphorus and sulfur in nanograms and picogram levels. Then coming to the principle, so the element in the sample is converted to ground state atoms by means of a flame or graphite furnace. By using graphite furnace we are converting the element into ground state. So for that conversion, a monochromatic light beam of specific wavelength from external source, say that like HCl, is passed through the flame or furnace containing ground state atoms. Now we are passing a light to the ground state atoms. That means we have to convert the ground state atoms into the excited state. These atoms absorbs radiation and excite. So when we are passing the light, so those atoms absorbs that light and it goes to the excited state. The amount of absorption is measured by decreasing in the intensity of light beam. So the amount of absorption is measured by the decreasing in intensity of the light beam. So the amount of absorption depends on the number of ground state atoms. If the number of ground state atoms are high, the amount of absorption of light is also high. Okay, and it in turn depends on the concentration of element in the sample. So here the amount of absorption depends on the number of ground state atoms, and in turn it depends on the concentration of the element in the sample. So it was given by A is directly proportional to C. That means amount of absorption is directly proportional to the concentration, where A equals to kV into Ct, where A is absorbance, C is concentration of the element, D is the width of the flame, kV is the absorption coefficient. So this is the schematic diagram of atomic absorption spectroscopy. It consists of a monochromator lamp and it passes to the flame. When it is passing to the flame, it comes into the ground state, and ground state which absorbs energy and it goes to the excited state. After excitation it absorbs some amount of the energy which is detected in a detector, and which gives the signal. Okay, so when the light of right wavelength passes through a cloud of ground state atoms produced by a flame or graphite atomizer, these ground state atoms absorb light energy and goes to the excited state. So when we pass the light of right wavelength through that cloud of ground state atoms, when you pass light to the ground state atoms, they absorb light energy and goes to the excited state. So we are applying light by a flame or graphite atomizer. So when these are gone to excited state, Unabsorbed radiation passes through the monochromator, which isolate the desired spectral light. So atoms absorbs the energy, light energy, and atoms are undergone excitation. Some of the unabsorbed radiation passes through the monochromator, which gives the desired spectral line. The isolated spectral line is resisted by a photodetector. So this spectral line is resisted by a photodetector. The output of the photodetector is amplified and measured on a meter or recorder. So the output is recorded, right? So here we are passing a flame or atomizer, graphite atomizer, in order to excite the ground state atoms. When the ground state atoms are excited, it absorbs some of the light radiation. So unabsorbed light radiation passes through the monochromator. When this passes through the monochromator, it forms a desired spectral line. So this desired spectral line, which gives the signal, so which was recorded in the recorder. So this is the instrumentation of the atomic absorption spectroscopy. Then coming to the applications of atomic absorption spectroscopy. So it has many uses in different areas of chemistry, such as clinical analysis of metals, in biological fluids and tissues such as whole blood, plasma, urine, saliva, brain tissues, liver, hair, muscles, tissues, semen. In some pharmaceutical manufacturing process, minute quantities of a catalyst. These are the applications. So applications are mainly in different areas of chemistry, such as clinical analysis of metals, in biological fluids and tissues, blood, plasma, urine analysis, saliva. So these are the some of the applications of atomic absorption spectroscopy. Next, coming to the flame emission spectroscopy, that is atomic emission spectroscopy. This is just quite opposite to the atomic absorption spectroscopy. So here atomic emission spectroscopy is an alternative to atomic absorption. So it is not as sensitive as atomic absorption spectroscopy, but does have the advantage of being able to analyze multiple elements. So in atomic absorption spectroscopy, we can analyze single element, but here in this atomic emission spectroscopy, we can analyze multiple elements. That is the main advantage of this atomic emission spectroscopy. So here the analyte solution is introduced into a flame, discharge or plasma to vaporize it. The high temperature atomization of the analyte drives the atoms to higher energy levels. Here also, when we are passing the light with high temperature or high energy, some of the energy is absorbed by the ground state atoms and they go to higher energy levels. So when they return to the ground state, they emit some of the photons of characteristic wavelengths. So here we are applying the light energy to the ground state atoms. So these ground state atoms absorb that light energy and undergoes for excitation. After excitation, they again return back to the ground state. So when they returns to the ground state, they emit photons. They emit some amount of the energy which is called as photons of characteristic wavelength. A high resolution spectrophotometer is used to determine the emission wavelengths. So when they return to the ground state, they emit some amount of the energy. So this energy is measured by using high resolution spectrometer, and thus the elements present. So by measuring the emission wavelengths, we can determine the elements present in that solution sample. Atomic emission spectroscopy is used when the material being analyzed has a large number of elements that are being analyzed. So first only we have said that, so this atomic emission spectroscopy is used to analyze the multiple elements. So here this large number of elements that are being analyzed by using atomic emission spectroscopy. Coming to the applications, so In the area of material science, this atomic emission spectroscopy is used in the area of material sciences. The electronics industry requires materials of high purity, and hence there is a need to monitor trace impurities levels in materials used for electronic components. So in electronic industry, they need high purity materials. So we have to remove the impurities. So for the removal of that impurities, we are using the atomic emission spectroscopy. So by using atomic emission spectroscopy, we can remove the impure metals or elements present in the materials, required materials. So in clinical laboratories for measuring the major cations like sodium and potassium. So it is also used as a ion selective electrode. Ion selective electrode means it selects particular ions only. So it is also used in urine analysis, and it is used to determine the arsenic and selenium in drinking mineral waters. So this atomic emission spectroscopy is used for determining the metals which is present in water, that is arsenic and selenium. And next, UV visible spectroscopy. So UV visible spectroscopy, so another alternative title for this visible spectroscopy is electron spectroscopy. So electron spectroscopy means it involves mainly depends upon the electrons. So another alternative title for this technique is electron spectroscopy, since it involves the promotion of electrons, that is promotion of electrons. So sigma, pi, n star electrons from the ground state to higher energy states. From ground state to higher energy states. Then coming to the basic principle of this UV spectroscopy, the absorption of visible light or ultraviolet light by a chemical compound will produce a distinct spectrum. When a light is passed through a prism, it produces a distinct spectrum, that means VCR. When UV radiations are absorbed, this results in the excitation of the electrons from the ground state to the higher energy states. When light is passed through the, that is UV radiation is passed through the ground state atoms, they absorb energy and they are excited to higher energy state. They revolving around this concept states that this theory revolving around this concept states that the energy from the absorbed ultraviolet radiation is actually equals to the energy difference between the higher energy state and the ground state. So here this theory mainly revolves that the energy from the absorbed ultraviolet radiation is actually equal to the energy difference between the ground state and higher energy state. So this is mainly works on the Beer-Lambert's principle. This law states that whenever a beam of monochromatic light is passed through a solution with an absorbing substance, the decreasing rate of the radiation intensity along with the thickness of the absorbing solution is actually proportional to the concentration of the solution and the incident radiation. So that is, this law is mathematically expressed as A equals to log I naught by I, that equals to ECL. That means here UV visible spectroscopy, it mainly follows Beer-Lambert's law. So that law we have already discussed earlier. So when a beam of monochromatic light is passed through a solution with an absorbing substance, the decreasing rate of the radiation intensity along with the thickness of the absorbing solution is actually proportional to the concentration of the solution and incident radiation. So therefore A equals to log I naught by I, that equals to ECL, where A stands for absorbance, I naught refers to the intensity of light upon sample cell, I equals to intensity of light departing the sample cell. Intensity of light upon the sample cell, that is I naught, where I is equals to intensity of the light departing the sample cell. C is the concentration of the solute. L is the length of the sample cell. E equals to molar absorptivity. So from the Beer-Lambert's law, it has been established that the greater the number of the molecules that are capable of absorbing light at certain wavelength, the greater the extent of absorption of light. That means greater the number of molecules that are capable of number of molecules that absorbs light at a certain wavelength will be the greater extent of absorption of light. So that is given by order of the type of transition, that is sigma star is greater than n sigma star, which is greater than pi star, which is greater than n pi star. So here UV spectroscopy mainly works on the Beer-Lambert's law. So we have already discussed Beer-Lambert's law. Beer-Lambert's law means when a beam of monochromatic light which is passed through a solution with an absorbing substance, intensity with thickness of absorbing solution is directly proportional to the concentration of the solution and the incident radiation, that is A equals to epsilon Cl or ECl. Then coming to the applications of UV spectroscopy, it has a wide range of applications in chemistry. So this UV spectroscopy, which is mainly used to detect the functional groups, which is present in the given compound can be detected by using this UV spectroscopy. It can be used to detect the absence or presence of chromophore in a complex. Chromophore which is present in a complex, that means functional group is present on either side in a complex compound. So this can be used to detect the extent of conjugation in polymers. So in polymers there is a conjugation or not. Conjugation means pi electron cloud. So alternate to double bonds. So it can be used to detect the extent of conjugation in polymers. It is used to identify unknown compounds. So if an unknown solution is given, we can identify the compound which is present in that given solution. So it also used to help determine the configuration of geometrical isomers. Cis alkanes are absorbed to a different wavelength, right? So here geometrical isomers, cis isomers, trans isomers, which can be determined by using this UV spectroscopy. It can be used to determine the purity of the substance. So here if the substance is impure, which can be determined by using this UV spectroscopy. So it can also be used for the analysis of food colorings, qualitative of wine. So it is also used in the kinetics, rate constant of reaction. So in cement industries, to determine the metal ions like iron, manganese, etc. So these are the applications of UV spectroscopy. So up to now we have learned about calorimetry, atomic absorption spectroscopy, atomic emission spectroscopy, next UV visible spectroscopy. So principle and applications of calorimetry, principle and applications of atomic absorption spectroscopy, principle and applications of atomic emission spectroscopy, and UV spectroscopy. In the next video we can go through the chromatographic techniques. So thank you.